Great, thank you. So let's recall what we did yesterday. I think there were 5 questions. So let's just briefly recall what they were. The first question was about structure. Structure and the definition of a Mach theta function. Question 2 was about this obstruction to modularity. Remember, we had a transformation law for f of q that involved omega of q, and also this integral, this sort of mysterious integral. So there was an obstruction to modularity. Question 3 was about the Andrews-Dragonet conjecture, which gave or a conjectural formula for the coefficients of f of q. Question 4 was about the Mach theta conjectures. And okay, so the Andrews-Dragonet conjecture, remember this was for an order 3 Mach theta function. The Mach theta conjectures involve order 5 Mach theta functions. And then the last question I asked was about indefinite theta functions. And I gave an example in order 7, though these will be more generally applicable, but for today I'll give an example in order 7. Michael has essentially answered question 5, but we still don't know exactly how that's related to the Mach theta function, so I will say a few words about this question. Okay, so around 2000, Zwegers wrote his thesis and another paper on Mach theta functions, and really answered a lot of, or opened the door to us answering a lot of these questions. So I'd like to give a modern definition of what we might say a Mach theta function is. Okay, so let's let f be, let's write it as f plus f minus. So let's let f be a harmonic Maass form. Of weight k. And as usual, I'll break f into the holomorphic part and the non-holomorphic part. Okay, so there's 3 parts to this definition. The first one is that f plus is called a Mach modular form. I think maybe I've said this in passing, and other people have mentioned this, but I don't think I've ever actually written down a definition of what a Mach modular form is. A Mach modular form is simply the holomorphic part of a harmonic Maass form if the non-holomorphic part is non-zero. Because remember, the space of weakly holomorphic modular forms sits inside the space of harmonic Maass forms. And if something's weakly holomorphic, we don't want to call it a Mach modular form. It's already a modular form. So if there's an honest non-holomorphic part, then the holomorphic part is called a Mach modular form. Okay. I think I've said this already, but I'll just say it again. CKF plus, or CKF, which is the same thing as CKF minus because CK annihilates F plus. This is called the shadow of F plus, the shadow of the Mach modular form. And then the third part of the definition is if K is either 1/2 or 3/2. So if the weight is one of these 2 special weights, and the shadow is a unary theta function, meaning one of those theta functions that Michael wrote down in the definite case, in the positive definite case, but with just one variable. So this matrix is just a 1-by-1 matrix. So that's what unary theta function is. So if the weight is one of these two special things and the shadow is of a special form, then F plus is called a Mach theta function. Okay, and one of the theorems that Zwegers proved, and I don't know that he ever wrote it down exactly like this, but well, he almost certainly didn't write it down exactly like this, but this follows from what he did. Ramanujan's 17 Mach theta functions satisfy this definition. So in other words, the 17 examples that Ramanujan wrote down in his last letter, they actually do satisfy the third part of this definition. There is some unary theta function that is the shadow of the Mach theta functions, such that when you complete them with this shadow piece, you get a harmonic Maass form of weight 1/2. And I will make a little comment here up to a rational power of Q. So the Mach theta functions that Ramanujan wrote down are like nicely integer powers of Q, but to get the transformations correct, you almost certainly have to change something. So for example, Q to the minus 1/24 f of Q, where this f of Q is the third order Mach theta function, this has shadow, and I'll just write this down, some constant times some n in z, minus 1 to the n plus 1/3 e to the 3 pi I n plus 1/3 squared tau. So that's the unary theta function. It's a weight 3/2 cusp form. Okay, so I believe this answers question 1. Because where is the structure? Well, the structure is provided by the theory of harmonic Maass forms. Now that we've put the Mach theta functions into this theory, well, there's your structure. There's your group action and all of that. Okay? Now, one thing that Ramanujan never did was actually prove that his 17 Mach theta functions satisfy his definition. And that was proved, I guess, about 10 years ago by Griffin, Ono, and Rowland. So Michael Griffin. So Ramanujan's 17 Mach theta functions satisfy his definition. And actually what they prove is that any Mach theta function from the standpoint of this definition will satisfy Ramanujan's definition. Remember, his definition was about cutting out singularities using more than one modular form. Okay, so let's move on to question number 2, this obstruction to modularity. So remember, what we were trying to do is see about this mysterious integral that shows up in the transformation law for f of q. And so here's another theorem of Zwegers. This is not in his thesis. This is in a paper that he wrote right before his thesis about the third order Mach theta functions. And it goes like this. So there are unary theta functions Let's call them G0, G1, and G2. And he writes down formulas for these, but I don't think they're super important for what we're doing today, so I'm not going to write them down. Such that, I guess I did write one down already. This one is G0. Such that, okay, I'm going to create a vector called h of tau. And this vector is going to have, well, it's going to start q to the minus 1/24th f of q. And then it's going to have two copies of omega. So it's going to have 2q to the 1/3 omega of q to the 1/2 and 2q to the 1/3 omega of minus q to the 1/2. You should think of these two, well, you should think of, maybe there are linear combinations of these two that would pick out just the even indexed coefficients or just the odd indexed coefficients of omega. And so there's sort of a natural way to think of omega sort of breaks into these two pieces. And then you need to add to this 2i√3 integral minus tau bar to I infinity. And then we'll put a vector of theta functions in here, G0 of w, G1 of w, G2 of w, transpose, over square root of minus I w plus tau dw. We've seen something like this before, right? Usually the non-holomorphic part of a harmonic Maass form, if the shadow is a cusp form, can be written in a form like this with this non-holomorphic Eichler integral. Okay, so there are unitary theta functions such that this vector satisfies h of tau plus 1 is equal to some matrix times h of tau. The matrix is simple. It's 24th root of unity, 0, 0, 0, 0, third root of unity, 0, third root of unity, 0. This is pretty obvious from the definition. These just come from these rational powers of Q. And much more interestingly, h of minus 1 over tau is equal to square root of minus I tau matrix h of tau, and this matrix is 0, 1, 0, 1, 0, 0, 0, 0, minus 1. And so this is a vector that transforms in this beautiful way under all of the matrices in SL2Z, because these two transformations generate SL2Z. Okay, so this, we could call this a vector-valued harmonic Maass form. Or as a corollary, if you restrict to just matrices in gamma 0, 2, then you don't need the whole vector f transforms by itself. So let's call this f tilde of tau equals q to the minus 1/24th f of q plus, I won't write it again, I'll just call it nh for non-holomorphic part. This thing is in h 1/2 gamma 0, 2 with some multiplier system, which I'll call nu sub f, whatever the multiplier system is. Okay, and I believe that answers our question about the obstruction to modularity, because, I mean, you can't get rid of the obstruction, it's there, but this answers how you deal with it, because what essentially is happening is that this function has the same obstruction to modularity. And when you add them together, the obstruction cancels. And so you get something that's truly modular at the cost of not having something holomorphic anymore. I think of this as a feature, not a bug. This is very interesting and rich. Okay, are there any questions so far? Yes. How do you get to gamma naught 2 from this? So what you can do, okay, so this is, let's call this maybe the matrix T 1101 that generates this transformation. This one would be S 0 minus 1, 1, 0 that gives you this transformation. You can write a set of generators for gamma naught 2 in terms of T and S. And then you can just, well, you're essentially just taking, however you write those generators in terms of T and S, you're now taking these two matrices and multiplying them together, and you can actually just do the calculation to see that the matrix that you get out of it is diagonal. So in other words, if you just take one of the terms, it goes back to itself instead of going to one of the other ones. So it's a fairly straightforward calculation. Yeah. Anybody else? Yeah. Well, so it's known that anything that satisfies this satisfies Ramanujan's original definition. Yes. That's this theorem. They proved more. I just sort of wrote it in this simple way. Yeah, they proved the more general thing, if I'm not mistaken. Yeah. Okay. These are the order 3 Mach theta functions. F appears in the last letter. Omega does not. It appears in the lost notebook. Yeah. There is a similar theorem for the higher order ones, and I will get to those in a minute. Yeah. Yeah. There is a similar theorem. Anybody else? Okay. So what's next? The Andrews-Dragonet conjecture. So this is also about f of q. So let's get to that. So the conjecture, I'll rewrite it for you, looks like alpha f of n equals 2 pi over 24n minus 1 to the 3/4. Sum c bigger than 0, 2 divides c of a c of n star over c, I 1/2 pi squared of 24n minus 1 over 6c. And then I messed up the definition of a c star yesterday, so let me fix that for you. So the part that was messed up was if c is even, or a 2c if c is even. So this was minus 1 to the c over 2, a 2c of n minus c over 2 if c is even. So that's a correction from yesterday. Okay, so this is the conjecture, and this was proven by Brinkman and Ono in 2006. The conjecture is true. I'm going to tell you about how this goes, but I'll put a little check mark here because, I mean, that explains question 3, but I am actually going to say a few words about this. I'll sort of tell you how the proof goes because I think it's interesting. And I'll try to point out what's hard about it and where the difficulties lie. Okay, so proof sketch. Okay, so for any k less than 1 and real S bigger than 1, we're going to let phi sk of tau be the following special function. So this is 6 over pi v to the k over 2 m minus k over 2 s minus 1/2 of pi v over 6 e of minus u over 24. This m is called the m Whittaker function. So m is usually written with like a mu and a nu. So this is the m Whittaker function. It's a special function. It satisfies a differential equation involving the hyperbolic Laplacian. And it is not annihilated by the hyperbolic Laplacian, but the eigenvalue that comes back involves s and k. And if you plug S equals k over 2 or 1 minus k over 2 in, you get 0. So this thing, if we specialize it, so if S equals 1 minus k over 2, then phi 1 minus k over 2k is annihilated by delta k. And so maybe this is a hint that there's something good here to look at. And the idea is that this S parameter gives us a little bit of wiggle room, and then eventually we will plug in this special value of S to get a harmonic Maass form. I actually have had this written up already without the S. I have had this function written up in a different way involving a Bessel function. It turns out that when you plug in S equals 1 minus k over 2, this collapses into a Bessel function. So this function is actually the one I wrote down in lecture 2 when we were constructing harmonic Maass forms using Poincare series. Okay, so we want, so when or if k is 1/2, which is the case we care about, we want to set S equal to 1 minus k over 2, which is 3/4. Okay, now I just told you that real S has to be bigger than 1. What we care about is when S is equal to 3/4, so clearly we have some work to do. Okay? All right. I'm going to leave my my questions up. If I like forget about that and start erasing these, you should squawk at me. Tell me to stop. Okay, so we want to analytically continue the Poincare series well, it would be P, and then we want this to be the seed, so phi sk tau. We want to analytically continue this to a neighborhood of S equals 1 minus k over 2. And we can do that using the Fourier expansion. So the Fourier expansion involves something that looks like a sum, c bigger than 0, ac of n star over c. Oh, I guess I need to divide c here. And then an I Bessel function, 2s minus 1 of pi squared of 24 n minus 1 over 6c. And that looks an awful lot like the thing we want. And let's see, if I plug s equals 3/4 into that, I do get 1/2. So if I can plug s equals 3/4 into here, then I'm done, assuming I can show that my Poincare series is equal to this f of q. But I have to do something about this sum, which it's not clear that it converges, and it's not even clear that it converges when s equals 3/4, because we remember that ac star of n, the best we can do individually is c to the 1/2 plus epsilon, and this just isn't good enough to give us the convergence of this sum. And so what we need to do is we need to study, or we need to measure the cancellation from sign changes of AC star of n. So AC of n is a real number. It's going to be positive or negative, and if we add up a bunch of them, well, there's going to be some cancellation that happens. So this is what we would use if we just had the triangle inequality and we just put absolute values on the inside. This is all we would get. But if we don't use the triangle inequality and we somehow measure the cancellation among these Kloosterman sums, well, then we can show that this sum converges at s equals 3/4. Okay? And so the object that you want to study is something like a sum, C, let's say C less than or equal to x of AC of n over C. And what you need to do is prove that this is a power saving smaller than you would get if you use the pointwise bound. So the pointwise bound, okay, if I just plug in c to the 1/2 here, then this sum, we're summing over things that look like c to the minus 1/2, which should give us something that looks like x to the 1/2 plus epsilon. Okay, but we need to do better than that by a full power saving, and so we need something like x to the 1/2 minus delta for some delta that's some positive number. Any positive delta will do. This is very hard. This is the hardest part of the argument, and it involves some really serious, really interesting math that I would love to tell you about if I had time, but it would really take us way off the beaten path. So this is very interesting. What do Brinkman and Ono do? Well, they use an argument of Hooley that ultimately comes down to an equidistribution result of CM points in the fundamental domain. There's an alternative method which involves the spectral theory of the hyperbolic Laplacian. And you have to study Maass cusp forms. It ends up being related to the Lindelof hypothesis for the L function associated to weight zero cusp forms. This is a very rich theory, and this is a hard way to do this. However, if you do carry this out, there's a theorem of Algren and Dunn, which they do get an explicit power saving estimate here. That's quite strong, and they actually use that to prove that, well, let me call this formula star. They prove that star does not converge absolutely. So it is a conditionally convergent series, which of course we suspected that because the best we could do absolutely was this, but that's not a proof, and they were able to prove that. And this fact that the sum converges conditionally was conjectured by Andrews in his PhD thesis. Okay, so using whatever method, one of these hard methods, we can prove this power saving estimate, and we can then plug in s equals 3/4. And what we can do is this. So let p of tau equal p of phi 3/4 1/2 tau. So I've plugged in s equals 3/4. Of course, not using the definition, but using the analytic continuation. Then p of tau is a harmonic Maass form of weight 1/2 for gamma 0, 2. And if we construct it to have the multiplier system for f of q, then it will have the multiplier system for f of q. And p has principal part q to the minus 1/24 at infinity, and no principal part at the other cusp of gamma 0, 2, which is 0. And that just comes from the actual construction of the Poincare series itself. Okay, so what are we going to do with that information? Okay, so what we want to do, let's let h of tau equal p of tau minus minus, let's call this f tilde of tau. Actually, I think I did call it that here. That's the completed version of f of q. So I'd like to show that these two things are equal, that p of tau equals f tilde of tau. So I want to show that h is the zero function. But I don't know that yet. I just know it's a harmonic Maass form. So what I can do is take the shadow. So let's let g equal c1/2 of h. So this is now a cusp form of weight 3/2 for gamma 0, 2 with the conjugate multiplier system of f. Okay. Well, I'd like to show that g is 0. So let's compute the inner product of g with itself. Okay? The inner product of g with itself is the same thing as the inner product of g with c1/2 of h. And if you remember from, what was it, lecture 2, maybe, Michael's lecture 2, the Bruinier and Funke pairing, this is precisely the definition of the Bruinier and Funke pairing. So this is GH. Okay, and then there's a description of what this comes out to. So this ends up being a sum over all the cusps of gamma, a sum over all n's less than or equal to 0, CG alpha of minus n, C plus H alpha of n. Okay, so this would be, what is this notation? So this would be the minus nth coefficient of g at the cusp alpha, and this would be the nth coefficient of h at the cusp alpha in the holomorphic part. But I just told you that that the principal part of h is 0, because the principal part matches exactly what's going on with f of q. This matches f of q at infinity. At 0, f of q looks like omega, which doesn't have a principal part. And so all of these numbers are 0. Okay, so we just get 0. Okay, look, so the inner product of g with itself is 0, thus g is equal to 0. So h is not really a harmonic Maass form, it's really a modular form. Is it weakly holomorphic? Well, no, it doesn't have a principal part. So it's actually a cusp form of weight 1/2 with this multiplier system. And you can show that this space of cusp forms is just 0. There aren't any things in there. So that proves the theorem modulo all of the hard details. Okay? Okay, any questions about that? It's a good place to pause. One immediate question you might have is, can you extend this to other Mach theta functions? We have this Andrews-Dragonet conjecture that's specifically about the order 3 Mach theta function f of q. So, well, let's talk about omega. So Sharon Garthwaite, this would have been just a couple of years after the Brinkman-Ono paper, she proved a formula for the coefficients of omega of q, using essentially the same techniques, because f and omega are related under some of these transformations. And so if you get a formula for f, you can probably turn it into a formula for omega. So that was a paper of Sharon Garthwaite. And so then you might ask about all of the other Mach theta functions. And actually, so maybe I'll put in a plug for myself. So this is coming soon. I'm hoping that we can put this on the archive in the next month or so. I'll put a question mark there. Coming soon, myself and a student of mine, whose name is actually also Andersen, but spelled differently than mine, and no relation to me. So coming soon, we have a paper in which we prove exact formulas for all of Ramanujan's Mach theta functions. So formulas for all 17 Mach theta functions using a uniform method meaning that we don't just compute each one individually 17 times and happen to put them in a very long paper. We do one calculation that gives all of them at once, which is kind of fun. And actually, okay, so there are other Mach theta functions other than these 17, and our method works for all of those as well. So it's fairly robust. Maybe I'll give you an example of one of the formulas so that you can look at it. Did not use the universal Mach theta functions, no. What's that? What kind of asymptotics do we get? So you can just take the first term of the exact formula, and that just gives you an asymptotic with as many error terms as you want. Take as many terms as you want in the series, and then you can just truncate, and then so if you take, for example, about approximately square root of n terms, then you can show that the error is bounded by a very small power of n, actually a small negative power of n. And this paper of Algren and Dunn, that's actually the main theorem of that paper, is an estimate for the error term after you take square root of n terms in the f of q formula. Okay, yeah, so I said I was going to show you one of these. Let me write it down. So, for example, alpha script f0 of n. So remember, this is our one of our seventh order Mach theta functions. So this looks like 2 pi over 168n minus 1 to the 1/4, sum over c is bigger than 0, sum Kloosterman sum, AC of n, I'll call it AC of n f0, over c, I1/2 of pi square root of 168 n minus 1 over 42c. And okay, these are order 7s, and you can see 7s all over the place. So yeah, maybe that's a hint there. Where AC of n f0 is defined in the following way. It's the square root of c over 21, sum b mod 42c, b squared congruent to 1 minus 168n mod 168c. Kronecker symbol, minus 21 on b, sine of minus pi b over 42c. So this resembles the f of q formula a lot, which is maybe not so surprising, especially knowing that we were able to do this with a uniform method. Probably all of the formulas coming out are going to look very similar. So for every Mach theta function, there is some capital N, which shows up right here. So this would be our capital N, which you could think of kind of like the level almost. There's some character. Well, this actually isn't a character. 21 on B is, but minus 21 on B isn't. But it's sort of a Legendre symbol showing up. And then there's some linear function of n, of little n, that shows up here, and then the big N shows up here. Anyway, there's a nice structure that shows up for all of these, and then you just sort of, all you need to know is the invariance, the big N, and this linear function and this character, and then you just sort of know everything. So hopefully that will be on the archive in the next month or so. So our argument uses this alternative method, the spectral theory of automorphic forms, which it's the hardest part here. It's the hardest part of our paper as well. If you just sort of assume everything converges, the formulas aren't hard to come up with. The convergence is always the hardest thing. Okay, so that's, we already put a check mark there. So let's move on to the Mach theta conjectures. remember these involve the order 5 Mach theta functions, of which there are 10, put into 2 families, indexed by 0s and 1s. I'm going to write down 4 of the Mach theta conjectures for you. I had this one written up yesterday. F0 of q is minus 2q to the, or 2q squared m of 1/5 q to the 10th plus theta 4 0 q to the 5th g of q. And I defined all of those things last time. I will not define every single piece of these, but I just want to show you the shape. There's f1 of q is minus 2q cubed m of 2/5 q to the 10th plus theta 4 0 q to the 5th h of q. H of q is there's the other Rogers-Ramanujan function, so it looks very similar to g. I believe g is supported on, or g is built out of q, powers of q that are 1 or 4 mod 5. H is 2 and 3 mod 5. So here's another one, big f0 of q minus 1 is equal to q m of 1/5 q to the 5th plus some other theta function, psi of q to the 5th, and then h of q squared. And then one more I'll write down for you is big f1 of q is q m of 2/5 q to the 5th plus psi of q to the 5th g of q squared. Okay, so if you recall from yesterday, so these g and h's are the Rogers-Ramanujan functions. These thetas and now psi, these are ordinary theta functions. So this part here is well understood. It's a modular form, no problems. Okay, these here are Mach theta functions that show up in the last letter. And these are specializations of a function that I wrote down yesterday called m, which is also sort of a Mach theta function. There are 6 more identities that look just like this for the other Mach theta functions. So there is a proof of the Mach theta conjectures by Hickerson. Remember I said that Andrews, so there were sort of 2 steps. First was Andrews and Garvin. And they reduced 10 to 2, meaning that if you want to prove all 10, you really actually just have to prove 2 of them, 1 in each family, and then you get the other 8 for free. And then the second step was that Hickerson proved 2, the number that he needed to prove. And these are both using Q-series methods that don't really use the theory of modular forms at all. And so I asked the question, Q4 was the question, is there a modular forms proof? Is there, now that we have this structure, and is there a conceptual proof of why these things should be equal to each other? So this was done, this was hinted at by Brinkman, Ono, and Rhodes. And basically they said, well, now that you have our main theorem, you should be able to just sort of plug this in to the Mach theta conjectures and do some calculations, and that should give you a proof of the Mach theta conjectures that uses modular forms. The idea is that, okay, or a lot of modular forms proofs come down to saying, well, if I want to prove that 2 modular forms are equal, I just need to find a space that they both live in, and then compute enough coefficients until I know that they're equal. Well, that's actually what happens here, except what happens here is that the space is 0, and so you don't compute any coefficients at all. But that's the spirit of this. And so in principle, Brinkman, Ono, and Rhodes said, well, now that you have our main theorem, you can just do that. So then Amanda Folsom actually did it, and she wrote a paper in which she actually went through all of the work to see, okay, well, how many coefficients do we actually need to compute? And unfortunately, it turns out that you need to compute too many coefficients. It's about 2 trillion. And it's too many for current computers to be able to do. So in principle, it works, but in practice, it doesn't. And so there's another approach to this, which I did a few years later. And what you can do is you can use the theory of vector-valued harmonic Maass forms with the Weil representation. And this is also a very cool theory that I would love to tell you about, but I don't have time. But you can kind of see it already in what we did with F and omega, right? There was a vector. We sort of needed to consider all of them together. We needed to consider a family of F, and then one copy of omega and another copy of omega. And once we had that vector, then we had a really nice transformation law. Well, similar things exist for the 5th and 7th order Mach theta functions. And if you then can put these into the theory that uses the Weil representation, which is basically just a description of how a vector transforms according to some totally explicit formulas, here's how this goes. So the 4 Mach theta functions over there to the left, that's why I showed you these 4, these fit into a vector in, let's say, H1/2. And I'll write this notation, but I haven't defined what it means, that this is some representation associated to some lattice. So they fit into a vector in that space, and so do the right-hand sides. The right-hand sides, right-hand sides also form a vector in this space. And so you've now found a space in which they both live, and now the entire game is to compute the shadow on the left and to compute the shadow on the right. This isn't too hard, and these are written down in various papers, and they're just the same. You can just show that they're the same thing. So now if I subtract these two sides, the left-hand side minus the right-hand side, I get a holomorphic modular form. And then all I have to do is compute the principal parts, which are fairly simple. They also cancel visibly. And so now I have something that's an honest modular form, a holomorphic modular form. And so let's say right-hand side minus left-hand side lives inside some space, which I won't define. And then there's a theorem of Skarupa that says that this space is just 0. There isn't anything in there. And so it reduces us to computing actually no coefficients because we just land in a space that's already 0. And so this gives a conceptual proof of the Mach theta conjectures and tells you why you might expect something like this to happen. Well, it's because both sides live in this space in which once you've canceled out the principal parts, there's just nothing left. In this setup, it turns out to be more natural to use the Weil representation. Yeah, I don't know if we use a different representation, what might happen. That was a case in which a lot of theory was written down already, and so I felt like, okay, if I can sort of shove it into this, then I know what to do. There's a theory of vector-valued modular forms with general representations, and I imagine that maybe you could write down maybe even a simpler proof if you picked an even better representation that's more natural for the thing. I just didn't know how to do that. So, yeah.
The other 6 also fit into...
Yeah, so that's a good question. What about the other 6? So I will point out, notice that there's a 0 and a 1 here. So I've already just taken 2, and once I prove it for these 2 only, if you use Andrews and Garvin, then you're just done, because this is one of each. But I didn't want to use Q-series methods at all. I wanted this to be a purely modular proof. So I actually don't even want to use this either. So it turns out that if you take 4 others, then the exact same proof works for 4 of the others. It's the same vector, same space, and the whole proof works out. And then the last 2, okay, well the last 2 it turns out are just really simple linear combinations of the other ones. And so you just get all 10. So yeah, you can get all 10 without actually using either of these 2 papers. Right, so let's put a check mark there. Are there any more questions about that before I move on to the last question? Okay. So now let's get to indefinite theta functions. And this connects to what Michael was talking about this morning. Okay, so indefinite theta functions. All right, so I wrote down a formula last time. I'll rewrite it. QQ sub infinity f0 of q. This is our 7th order, one of our 7th order Mach theta functions. So this is the sum r and s greater than or equal to 0 minus the sum r and s less than 0 of -1 to the r plus s, q to the 3/2 r squared plus 4rs plus 3/2 s squared plus 1/2 r plus 1/2 s. And I mentioned that this is an indefinite quadratic form. So what do we do with that? And Michael told us what we're supposed to do with that. He told us about this theory. And so in the last chapter of Zwegers' thesis, after he works out all this theory of indefinite theta functions, he actually does this example, and all of the 5th order and all of the 7th order Mach theta functions have formulas that look like this. And if we rewrite this, we get the following thing. So 2 eta of tau, zeta 14 q to the minus 1/168 f0 of q equals sum over all news in 1/14 e plus z2. Okay, what is e? E is just the vector 1, 1. Okay, so now I get the sign of some bilinear form, b nu c, c1. Okay, I should define these things. I'll define them as I go. So what is the bilinear form? Well, we're going to take a matrix 3, 4, 4, 3. And quadratic form, q of x, is x transpose ax. The bilinear form, 1/2 this, x transpose ax. The bilinear form xy is x transpose ay. C1 is the vector -3, 4, and C2 is the vector -4, 3. This is all written down in Zwegers' thesis, so maybe you don't need to write all of these details down. You can just look this up. But let's just look at it together. So I need to subtract the sign of b nu c2. And then the most interesting part is this, e to the 2 pi I quadratic form of nu tau plus 2 pi I bilinear form nu 1/14 e. And that resembles one of the indefinite theta functions that Michael wrote down. And so when you have this whole theory, well, okay, so let's do this. So in Zwegers' notation, this thing is called theta 1/14 e 1/14 E. I think Michael in his notation, he put the A, B at the top and the C1, C2 at the bottom. In Zwegers, I think it's actually the other way. This is A and B, and the C1 and C2, he just actually drops from the notation, and they're supposed to just be understood from context. So that's what's going on here. So theta of tau, and it turns out you can show that this is, or he shows that this is 2 zeta 14 q to the minus 1 over 168 eta of tau f0 of q plus, so this is the completed thing. This has a non-holomorphic part, so 2 eta of tau times zeta 12 inverse r 13 over 42 minus 1/2 21 tau plus zeta 12 r 41 over 42 minus 1/2 21 tau. And I got to define more stuff where RAB of tau is this familiar thing. It's the non-holomorphic Eichler integral of some function GA minus B of Z. So this is just some unary theta function. In this case, it will be weight 3/2 over square root of minus I tau plus Z dZ. And I won't write down the definition of G. Okay, so what's going on here? This is the holomorphic part, the thing we really care about, and it resembles part of this indefinite theta function. And if you take the completed indefinite theta function of Zwegers, well, okay, you get the the holomorphic part, as we wrote over there, and you also get this non-holomorphic part, but it looks very nice. It looks exactly like a non-holomorphic part should look. It's an Eichler integral of a unary theta function. Notice that there's etas here and here, which drop out. You can put them on this side, and the transformation law becomes very nice. So it turns out the right thing to do is to take actually all three of the 7th order functions, f0, f1, and f2, and to do this to all of them and form a vector, and they transform with respect to some representation. And so that really answers our last question, which is what are we supposed to do with these indefinite theta functions? And the answer is, well, complete them to harmonic Maass forms, and this lets us study all of the, well, at least in Zwegers' thesis, all of the 5th and 7th order Mach theta functions, which are the ones that we haven't covered yet. And those results play into this, theorem here, and they play into actually basically everything I've talked about today. So this really is the starting point, even though I did it at the end. This is how we realize all of the Mach theta functions as holomorphic parts of harmonic Maass forms. So that seems like a good place to stop, so I'll stop there. Thanks.
Okay, thanks a lot, Nick. Yeah, there's a question.
Yeah, so why is there a distinction in between third order and fifth order Mach theta functions for these conditions? Why does he use indefinite?
Oh yeah, why does he use indefinite theta functions for the 5th and 7th order, and why does he not do it that way? He does it a completely different way for the 3rd order. I don't know, and I hope you can answer that question. Because I think you said you and Frank Garvin are working on something like that, right? So yeah, I don't know why he doesn't include the 3rd order Mach theta functions in his thesis. I mean, I know he already sort of explained things about them in a different paper, but it seems like they should fit nicely into the theory as well, and I don't know. Anybody else?
All right, so thanks a lot. We'll break for lunch and resume at 2:30. Thanks a lot.